Do you remember learning multiplication tables in school? You lay out the numbers, say 1 through 6, going across a table, and put the same numbers going down the side. Then you fill in the product of each pair of numbers in each square. Now let's say we want to teach a computer how to multiply. We can use a neural network to do this by providing some answers in the table, then leaving the rest blank. A neural network learns by passing data through layers of elements called neurons, which try to mimic what happens in our brains. Here, we pass in 2 numbers to the neural network, and it returns another number. If it gets the answer right, it gets rewarded. Otherwise, it gets penalized. So, if we pass in 3 times 2 and the neural network returns 8, it gets a penalty. The next time, it returns a new number, say 7, and gets a smaller penalty. This continues until it gets the answer right. Now, you might wonder, how can we know the neural network will eventually get the answer right? There's actually a really deep result about this called the universal function approximator theorem. This result, which has been proven mathematically, says that with enough neurons and enough layers, a neural network can approximate any function. So we know a neural network can learn multiplication just like we did in school. But if you think carefully about this theorem, you'll notice we said one key thing: with enough neurons and enough layers. So even though this theorem is true, in practice, we might need neural networks that are too big to be useful. However, we have many examples where relatively small neural networks work surprisingly well. So, what's going on? This is where physics comes in. If you think about the multiplication table, there's one key thing that simplifies the problem. When you multiply, the order doesn't matter. In other words, 3 times 2 is the same as 2 times 3. This really simplifies the learning process for the neural network. It cuts the possibilities in half. What we just described is what mathematicians and physicists call symmetry. In other words, multiplication is said to be symmetric with respect to its arguments referring to the numbers being multiplied. Symmetry is one of the most powerful principles in physics in particular, and there are many more examples of it. In Newton's law of gravity, for instance, it doesn't matter where you are on the Earth. All that matters is how far away you are from its center. The force of gravity is symmetric everywhere on Earth. In machine learning, most of the data we want to learn also has a lot of symmetry. This is because data is something measured in the real world, and the real world obeys the laws of physics. In many cases, this makes it possible for relatively small neural networks to do the job. In addition to symmetry, there are other principles in physics which contribute to this too, with names like locality and low polynomial order. We won't dive into these now, but the idea is the same. They simplify the data and help neural networks learn. At the end of the day, there's not one definitive answer to why neural networks work so well. The magic involves everything from big data, key algorithms like backpropagation, and powerful computers. But of all these components, there's no denying that physics plays a big role in helping neural networks learn.